A lot of them sound very similar titles, though. There's a lot of relationships between the sections. It's not 5 individual things. And in fact, the first one, squares and square roots, we started talking where some of you started working with last time. You started doing the explore the math, and maybe some of you missed or didn't quite get the point out of it of what you intended, but that's okay. It started you thinking about making squares and how many numbers, what numbers would form a perfect square, what numbers wouldn't form a perfect square. Hopefully you discovered, say if you take 4 objects, you can make a square out of it. But if you take 5 objects, you can't make a square out of it. If you have 6, you can make a rectangle, but you can't make a square. Numbers that you can make a square are called perfect squares. 1, 4, 9, 16. What did we say the next one was? 25. What was the next one after that?
36.
There's actually one that's before this that it's hard to think of it as a square, but there's another perfect square below 1. It's actually 0. You can make a square that's 0. A perfect square is something where something times itself gives you that number. 1 can be written as something times itself, right? You can write 1 as something times itself. What can you write 1 as? Here, let's have a different page because this would be much better. New page, and then we can use the grid here. A perfect square. 1 is a perfect square because you can make a square that's 1 times 1. The area of that square is 1, right? You can make a square that's 2 times 2. What's the area of that square? This is 2 times 2. The area is 4, right? You can make a square that's 0, although I can't draw it, right? A square that's 0 is not that. A square that's 0 is, you won't even see it, right? It'll just be right there. 0 times 0, what's the area of that square? 0, right? I know it's not there, but it's hard to think about. 0 is a perfect square. 1's a perfect square. 4 is a perfect square. Any number you make here is if you draw a square, the next one's 9, 16. We're going to have to do the next down here, but 25 is the next one after that, I guess, right there, right? Did I miss one? I made too many. Got to do that one again. There's 5. 36. Okay, you made that one in the activity you did last time. And you can keep going, right? But we're not going to keep drawing them all here. But as long as you understand the concept of, for something to be a perfect square, it has to be able to be expressed as something times itself. Thank you. That helps closing the door. Part of what you have to get out of this first section is the harder thing to see that maybe they were hoping with that Explorer you might notice, but it's hard to notice, is about the factors, about how the factors of a number are related to whether it's a perfect square or not. So let's try and write each of these as factors, as products of prime factors. If you don't have a piece of paper, maybe you could find one right now and draw those 6 squares and put those numbers in there. We're going to write their factors right inside there. 6 times 6 is that one. 5 times 5 is this one. Okay, I'm going to pause this one here. If you're going to write the factors, you can use a dot instead of a time sign. Mathematicians are lazy, and this is just too much for them to write, this x. So instead, sometimes they write a dot. That's not that they're lazy, it's that an x gets mixed up with an x if you start using variables. So you can use a dot to mean times. What's another one? What about 9? If you write it as factors, prime factors, what do we have? What do you have? 3 times 3, right? Now, the harder one is if we write 16 as prime factors, it is 4 times 4, right? But prime factors means you can't break them down anymore. If you're factoring the number 16, whether you're using a factor tree or a factor stack, right? Remember those 2 different ways you can come up with the factors? If you're factoring the number 16 and you start to break it down like this, divided by 2, you get 4. Divided by 2 again, you get 2. And you get the 1, right? Its factors are 2 times 2 times 2 times 2. Like that. What about 25? What is it as a product of prime factors? What's it? 5 times 5, right? It only has 2 prime factors, 5 times 5. And the number 36, if we write this as product of prime factors, Can you think about what it is as prime factors? I'm gonna do this one not as a stack like I did up here. That I'm calling a factor stack. Here you can make a factor tree. It doesn't matter which one you do, whichever one you like better. If you like making factor trees here, whichever way you start, you split it up into two things that multiply, divided by something. 6 times 6, 2 times 3, 2 times 3. The prime factors of 36 are 2 times 2 times 3 times 3. Now let's pick some numbers that are not perfect squares. Give me an example of a number that's not a perfect square, or some numbers. 2, 5, all those ones, right? I want one slightly bigger that we can actually factor. 26, sure. Not perfect squares. All of the ones you guys just gave me are not perfect squares, but let's pick a bigger one like, how about 28? Let's do 28. For example, 28 is not a perfect square. If you were to factor the number 28, we want to try and notice now, how are the factors of perfect squares different than the factors of non-perfect squares? So let's factor a few perfect squares. Let's factor 28, let's factor 20, and let's factor, I don't know, 60? How about 60? Well, 60 is going to be similar to 20, but can you factor those three numbers? I'm going to pause this while you factor those three numbers. Okay, so once you have these factors, I want us to look at what's the difference between the ones that are not perfect squares, as in, how could you tell from this whether the number is a perfect square or not? That's what we want to be able to do. That's one of the big goals, and it's one of the hardest things in this unit, is how can you tell from the prime factors whether something's a perfect square? If you look at the differences between the two things, what do all these prime factors, prime factorizations, what do they all have in common that these don't have? That's what we want to think about right now, okay? What do those all have in common that's different than those? What do you think? Same numbers, like this has 2 2s, 2 3s. This has 4 2s, is that okay? Same number, this has survives. What about this one? This doesn't have all the same numbers. Is that what you meant? It has what? It has like pairs, like a pair of 2s and a pair of 3s? Is that what you mean? 2 2s and 3 3s? 2 2s and 3 3s would not be a perfect square.
So it has to be even for each side.
What do you mean what has to be even? This is good comments and questions here. You guys should be listening, right?
So it has to have like each number has to be even at the bottom.
Each number has to be even at the bottom. This is a good way of putting it, right? Because you notice how this is 6 times 6? This is 6 times 6. Each of those 6s has a 3 in it, and it has a 2 in it. Does that make sense? Because if you take the factors and regroup them, as long as you have them in pairs, even numbers, you can split them up equally, right? So let's take your case of 2 2s and 3 3s here. If we were going to make a square here, so, whoops, that's not good. If we're going to make a square and think we're going to try and make a perfect square out of this, so let's not use the grid because it'll confuse us, but if you have 2 2s, you could put one of the 2s here and one of the 2s here. If you have 2 more 3s, you could put one of the 3s here and one of the 3s here, but you're going to have a leftover 3. You can't put it in both sides, right? If I multiply one of those two sides by 3, I can't put it on the other side, right? This is going to be a lot longer this way now, right? This is not going to be a square because it's going to be 3 times as long this way, right? But 1.5 times 1.5 doesn't give you 3, right? You can't split the 3 up into 2 whole numbers, right? You can make a square out of it. It's just that it won't be a whole number on the side. You will be able to make it. There is a number that would work, but it won't be a whole number, and then that's not a perfect square. Perfect square means you have to make it into a whole number. Let's make a list here of the first. Make a list of the first. I don't know how many perfect squares can you do. 1, 4, 9, 16. See how far you can go here with this, and then let's just make up some sets of factors and see what they give us. What's the next one after that? 49, 64.
72.
Not 72. 81. 100. 11 times 11, 121. 144. Let's see what, let's just pick some prime factors and see, because your theory there was, this is not a good theory because this thing's frozen now, but let's see what your theory is about, very strange. Well, let's, your theory was they had to be an even number of each prime factor, right? Wasn't it? Like each of these you can put them in pairs, right? Pair of 3s, pair of 2s. But this has a pair of 2s, but there's an extra, right? There's an extra 7. This has an extra 5. This has an extra 3 and 5. You can't pair them up to make the same number, but if you have 2 2s and 3 3s, you can do this, right? You can put 1 2 here, and 1 2 here, and 1 3 here, and 1 3 here. And when I multiply each of those, what do I get? 6 times 6, right? Once you have the prime factors, you can start to multiply them out again. It has to be a perfect square if you can make it 6 times 6, right? That's the definition of a perfect square, 6 times 6, a number times itself. But if you had this extra 3 here, where do you put it? Do you put it with this one or this one? You can't, right? You can't make it into two of the same numbers. Let's make another number here by writing a group of, let's say we had 2 times 2 times 2 times 2 times 3 times 3 times 5 times 5. Is that a perfect square? Let's call this A. A is equal to that. Is A a perfect square? What do you think? It is? Why is it a perfect square? Are you guessing or you have a theory here? You're guessing. Is this going to be a perfect square? You have to look at, if it's a perfect square, we have to be able to say it's something times itself, right? It has to be something times itself to be a perfect square. If you look at what the factors are, I can put, you can group them evenly, right? I'm going to cheat here and I'm going to say copy, and then I'm going to paste this again because I want to be able to work with them here. So there's my numbers. I can take these ones, right? I have a pair of 2s there. I can put one of each pair. This pair, I can put this one over here, and I can put this one over here, right? And I got another pair here, so I can put this one here, and I can put this one here, right? And then what about the 3s here? You got a pair of 3s, so this one can go here, and this one can go here. You can group it all equally, right? And one of the 5s can go here, and one of the 5s can go here. If it happens that they occur in pairs, or in other words, there's an even number of each prime factor, then it is a perfect square because you can group them. What does this multiply out here? 2 times 2 times 3 times 5? What does that multiply out? 2 times 2 times 3 times 5 is 60. This is 60 times 60, right? 60 times 60, what does that give you? 3,600 is a perfect square. It has to be because the factors occur in pairs. If there was an extra something here, let's say there's an extra 5, where does it go? Does it go here or here? You can't put it in both places if there's only one of them, right? This would not be a perfect square because there's an extra, an odd person out here, right? If they occur in pairs, or in other words, if there's an even number of each of them, you can split them up. Okay? You try it for any number you want. If you write out a set of numbers where they're all an even number, it'll end up being a perfect square. I want you to pick whichever one you want. Like, write out a set of prime factors and make it occur in pairs, and then you can see what results here. How could you check on a calculator whether this is a perfect square? How could you check on a calculator? Do you know? If you were to take your calculator, one of your 3 calculators for some reason I have here, but if you take your calculator, there is a button on there that lets you check. It's called the check if this number is a perfect square button. Do you see that on here anywhere? Or do you have a comment? It's this one. You see how this thing here, this symbol right here, that symbol means push this button and check if it's a perfect square, because if you get a whole number, it's a perfect square, and if you don't get a whole number, it's not a perfect square. If we put in that button, and then I put a number like 9, what do you think it's going to tell me? It's going to tell you? It's going to be a whole number. It's going to tell you 3. If I do that button, I put 16, what do you think it's going to tell me? Somebody else tell me. What do you think it's going to tell me? It's going to tell me 4. So this symbol is called the check if it's a perfect square. It's not called that. I'm just being weird. What is this symbol called? It's the square root button. That's a square root button. If you do the square root of 3,600, what is it going to tell us?
60.
It's going to tell you 60. It's telling you the length of the side of a square. The square root is saying, if you have a number like 3,600, how big's the square? How big's the side of the square? All right? That's what that button is. On a calculator, it shows it this way. You might have a fancy calculator that shows it in the way you write it. Here's a fancy virtual calculator that shows it the way you write it. This one, when you push the square root button, and then I put 3,600. What's the difference with how it's writing it there? It has what? It puts it under the line. This is how you write it when you do it. You can write it like this if you want, but that's the normal way to write it. And it tells you 60, right? If you want to say square root of a number like 49, you do it like that. Okay? What's the square root of 49?
7.
Don't tell him.
7.
7. I'm glad you're relying on him. See how he's paying attention now because I caught him not paying attention before? It's okay, I'm recording it, but I'm not using any names, right? So it won't be published online who wasn't paying attention, okay? That's important, right? I don't want to permanently record it forever who wasn't paying attention. It is, you have to find it on your calculator. On this kind of calculator, the ones that you guys can borrow from me, it's right above the button that says x squared. You have to use the second function button first, okay? You have to push second, that button, a number like 100. What would it tell me if I put a number like 100? What's it going to tell me if I put 100 in there? 10, it will. What's it going to put if I tell you a number like 103? It's going to tell you a number that's not, this is not a perfect square, because when you find its square root, it's 10 and some other stuff. You can't take 103 objects and make them into a square. But you can take 100 objects and make them into a square, and it's going to be 10 by 10. You can check on the calculator whether something's a perfect square by doing that. If you get a decimal number, it's not a perfect square. If you get a whole number, it is a perfect square. Comment?
What if you had the prime numbers small numbers of 6, 2, and 3? Does that work? Like if you took 2.
6, 2, 3? Yeah, because this is the same as this, right? 6 times 6, it's a perfect square. It's 36. All right. Can we look at this 3.1 now? Let me tell you what I would like you to, restart later. Can we, I know it's hard to focus for 19 minutes and 48 seconds. I understand that. Okay? Just, again, how this class works, this will never get to 55 minutes and whatever. Like, I'm never going to, the lectures in here are short, but you need to pay attention while they are. Okay? I know that probably research shows that the average person who's 13 years old, this is beyond their attention span. I know I'm much older than 13 years old, but my attention span, I think, is less than this as well. So bear with me. This is 20 minutes now. But it's never going to get up to 55. So you need to be able to focus for a short time. Some of you did this last time. Essentially what they're saying is they want you to make a rectangle. If you were struggling with it last time, take those numbers and make a rectangle that shape, and then try to rearrange them to make a square. I think what you found is this was a no, this was a yes, this was a yes, and this was a yes, and this was a no. Okay? If you make a rectangle 8 by 2, you could rearrange it. How you could rearrange it? A rectangle is 8 by 2. What could you rearrange it to be? 8 by 2? 8 by 2 is, I mean, you're going to have 16, right? 1, 2, 3, 4, 5, 6, 7, 8 by 2. There's one that's, you're going to have 16 in total. And how could I rearrange that to form a rectangle? I could take that bunch right there and do this and put it right here, right? Is that a square now? It is a square, right? If I factored that all the way, I'd get 2 times 2 times 2 times 2. That one, perfect square because you can make it into groups. All right? When they ask you here, and some of you weren't sure because what do all the perfect squares have in common? Look at their prime factors. I understand this is a stretch to discover this on your own. The Explore the Math are intended for you to discover some things on your own. This is a tough one to discover on your own, but now that we've looked at it together after you've tried it, you could probably say something here about what the prime factors all have in common, right? Couldn't you? What do all the prime factors have in common for perfect squares? What do they have in common? What do you think? Because you're paying such good attention. Got to pay attention in here, okay? Or at least just stare down at your desk and not make it obvious you're not paying attention, right? You got to come up with, I'll let you off the hook, okay? You got to come up with what the difference is there. We are not going to use tiles all the time to determine if a number is a perfect square. You have two strategies for deciding if something's a perfect square. If you are taking notes, and we made these nice notes here, mine look terrible by the way, but I'll at least finish it up with a good summary at the end here. This is what I would put. 2 ways to tell if a number is a perfect square. Actually, 3 ways. Way number 1. If I ask you, if I give you a number like 36, is that a perfect square?
Yes.
How do you know that? We just told you that's one you know, right? If it's a small enough one, you might know. Here's way number 1. I'm going to say you just know. You just know. I.e., small number, you've seen it before, right? Small number, seen it before, right? That's only going to work for small numbers. Way number 2 is, what are some other ways we can tell if a number is a perfect square?
Square root button.
Square root button. Use square root button on calculator. Okay, that button. Square root. What's way number 3? And this one you have to be able to do. It's the hardest of the 3 because you got to do lots of factoring, but what's the third way you can tell? Yeah, split it up, divide it up, find out all its factors. Factor the number. Factor into prime factors. And how do you decide from that whether it's a perfect square or not? If prime factors occur in pairs, then what's true about it? If they occur in pairs, then what's true about the number? Then yes, it is, right? If not, it's a no. Okay? This is what you need to know from that first section. Okay? Which ones of those things do you think people are going to remember even if they don't do any practice between now and the day we do the test? Which ones of these do you think people are going to know how to do on the test?
1 and 2.
1 and 2. Which one do you think they're going to forget? This one they're going to forget. That's the one that you have to find some way of figuring out for yourself. Some people are very good at learning by sitting there and watching the teacher do stuff on the screen. And you may well, test comes and you know this. You may be one of those people. Some people are not going to learn it until you do something. Most people are in that camp, right? You don't learn by watching, you learn by doing. So you got to do some stuff now. And what it is you could do is you could work through these examples, right? There's a couple of examples in here. The study guide, looking through some of the study guides that you guys have handed in, they look like they're pretty well done. Sometimes some people have just an answer. They don't really have much explained. These ones I realize you can already tell whether they're a perfect square. This is telling you factor the numbers and explain how you can tell. Explain how you can tell from the prime factors. Don't just say yes, no, no, yes, no. The key is being able to explain how you can tell from their prime factors. So this would be good if it was nicely written out where this you had its factorization, this you had its factorization, and this you had its factorization, and then here you explained. Okay? It says here to draw a square. I actually put the drawing in for you and even gave you a little hint here about which ones are perfect squares. You know these show you know questions? The idea is that you show how you know. You show you know. In the end, you have the answers, the very end of the thing. If you look at the end of your booklet, there's the answers to the show you know questions, so you can check as you go to make sure you know. That's the idea of what you're supposed to be doing, right? You should be checking these and marking them as you go. I noticed that some people don't even read the textbook when you are working on these. If you want to do that and you're sure you know, that's fine, but that's what that hint is, right? Have a look at the book if you're not sure. Determine the area of that, right? The area is going to be, the area of a square is the length of the side squared. Area is length of the side squared. There's a hint right there. Can you work on section 3.1? The goal would be we got to get section 3.1 done for next time. You got about 20 minutes or so right now. You can get a good chunk of this done.